Thank you for the very nice introduction, Patricia, and thanks to all of the organizers for the invitation. As many other speakers have said, it's of course a shame that we can't be in Chile in person, meeting each other and discussing interesting things related to black holes, but it's definitely a mercy that we're able to have this event remotely. So in my talk today, I'll be discussing tidal disruption events, or TDEs. These are powerful multi-wavelength flares of radiation that are produced when stars wander too close to supermassive or intermediate mass black holes. But and while I'll discuss the physics and hydrodynamics of these flares and the details that set the observable signatures they have, my main motivation and focus for this talk will be using tidal disruption events as tools, questionnaires, if you will, to perform a demographic survey or census of the massive black holes that reside in galactic nuclei. So since this is a slightly longer talk, I'll begin with a brief outline so that you know what's going to happen. The beginning of this talk will be an overview of TDs, both from a theoretical and an observational perspective. To get things started, I think this sort of classic cartoon by Martin Rees in his 1988 Nature paper is a great starting point. So in this cartoon, you can see the basic sequence of events in a tidal disruption flare. Initially, you have a star that is in hydrostatic equilibrium. It's scattered onto a nearly radial, nearly parabolic orbit in a galactic nucleus. In the center of the galactic nucleus, you have a massive black hole. It could be a supermassive black hole, maybe it's an exciting intermediate mass black hole. But regardless, there's a critical radius known as the tidal radius. This is just the radius of the victim star times the cube root of the mass ratio. And if the star's pericenter falls inside this tidal radius, the star is unable to maintain itself in hydrostatic equilibrium. It will get torn apart and spaghettified into very elongated, dynamically cold debris streams. These debris streams have typical eccentricities of order 0.99 or greater. About half of them are unbound. Half of the mass is unbound from the black hole and flies off to infinity, but half of the mass remains bound and eventually comes back to pericenter to begin dissipating its orbital energy and emitting radiation that we can see here on Earth. These events are, in principle, very simple because they depend on only a small handful of underlying parameters, which I've highlighted in the bottom of this cartoon. So 4 parameters that we know these events depend on in a strong sort of leading order kind of way are the mass of the black hole, the spin of the black hole, the pericenter of the star's orbit, Rp, and the mass of the star, m sub star. I've written these 4 key variables in blue. 2 other variables which may or may not matter so much are the radius of the star, r, and the misalignment angle, I, between the plane of the star's orbit and the equatorial plane of the black hole. I say that these may not matter so much because spin-orbit misalignment is still a bit of an open question in TDs. I'll get into that in a little bit. And while the radius of the star certainly matters quite a bit, as long as we're talking about main sequence stars, if you know the mass, you know the radius to within a decent level of approximation. Then there are other properties, which I've highlighted in red. You have the metallicity of the star, the spin of the star omega, and the age of the star along the main sequence T. These affect the properties of the tidal disruption at some level, but they're not leading order effects. So in principle, observing and modeling tidal disruption flares seems like a very good way to get at the masses and spins of supermassive black holes in quiescent galactic nuclei, because there are only a handful of parameters other than these 2 which we care about that set the properties of the flare. But as you will see as this talk goes on, the devil is very much in the details. So over the course of this talk, I will discuss ways in which the mass of the perpetrator black hole is encoded in the light curve and spectral energy distribution of a tidal disruption flare. I'll discuss ways in which the spin of the perpetrator black hole is also encoded in these observable properties. And then towards the end of the talk, I will focus more on how, even if we don't understand how to get masses and spins from individual tidal disruption events, distributions of masses and distributions of spins are encoded in populations and the observable properties of populations of TDs. And I'll conclude the talk with a few thoughts on what TD science will be able to contribute to black hole demographics in the relatively near future. So to get this overview of TDs started, let's begin with a theoretical hydrodynamic simulation of the process of tidal disruption. So this simulation, which was performed by my collaborator Kimi Hayasaki a few years ago, is a smooth particle hydrodynamic simulation using post-Newtonian gravity. Here we're looking at the aftermath of a star getting disrupted by a spinning supermassive black hole of 10 to the 6 solar masses. The black hole is spinning quickly, which led to some precession of the star's orbit around the black hole spin axis. But what you saw in this simulation was that as soon as the elongated debris stream begins intersecting itself due to relativistic apsidal precession, it dissipates its orbital energy, heats itself up, and relatively quickly circularizes into this puffy accretion torus that extends to a few times the tidal radius for the black hole and star combination in this problem. That's one theoretical simulation of tidal disruption events. There's a lot more going on there that I'll come back to in a minute. But I'd like to also show you guys some a basic survey of observations of TDs. So at the present moment, our rate of TD detection is dominated by wide field optical time domain surveys like PAM-STARS and Assassin and ZTF. And what you can see here is a compilation of the bolometric optical light curves. So optical light curves with some fitted bolometric correction for a sample of about a dozen recent tidal disruption flares. What you can see is that these are very luminous events. They rise to peak luminosities of order 10 to the 43 to 10 to the 44, maybe even a little higher, ergs per second. The rise time is typically weeks to maybe a month. And then the optical and near ultraviolet radiation decays over longer periods of time, months to years. One thing I should emphasize is that tidal disruption events are relatively rare flares. We'll go into a little more detail about the stellar dynamical processes that set their rates later on. And as a result, observers who are looking for TDs need to be very careful to avoid false positives like AGN variability or nuclear supernovae. So the vast majority of events that have been tagged as tidal disruption events in current time domain surveys, and there are a few dozen of these now, are occurring in the nuclei of otherwise quiescent galaxies. So one thing to emphasize is that the properties of these flares really give you a window onto a population of massive black holes that is hard to study through other means. These are massive black holes that are far away. If the peak luminosity is 10 to the 44 ergs per second, you can see these to redshift of order point a few, so much too far away to get dynamical mass measurements. But they're also happening in quiescent galactic nuclei, so you can't constrain their masses and spins using the usual tools of AGN science. Okay, the left panel was a compilation of sort of bolometric light curves. But in reality, observed TDs are multi-wavelength flares. They emit photons across the electromagnetic spectrum from radio wavelengths all the way up to very hard X-rays. What you're seeing here are a couple of different light curves for the same tidal disruption event, Assassin 14Li. In the top panel, you can see that in this flare, the near ultraviolet and the associated optical luminosity was very similar in magnitude to quasi-thermal soft X-ray emission, which was seen simultaneously. And in the bottom panel, you can see that there was also a non-thermal component, probably coming from some sort of forward shock from ejecta slamming into the ambient interstellar medium in the nucleus of this quiescent galaxy, which was detected at radio wavelengths. Now, there's a lot we don't understand yet about tidal disruption events. From a purely theoretical perspective, we don't exactly understand the process, the efficiency, and even the question of whether or not these elongated debris streams are able to circularize into a standard, by which I mean a quasi-circular and axisymmetric accretion flow. The problem here is that the dynamic range of the TD problem is very challenging to simulate self-consistently from first principles. So essentially all existing hydrodynamic simulations of tidal disruption cheat a little. The process of the disruption is itself well converged and well understood, but the aftermath, in which debris streams fly out from pericenters of 10 gravitational radii to apocenters of thousands of gravitational radii, and then come back and dissipate their energy, is not by any means fully converged. And it seems plausible, in my mind likely, that the efficiency of the circularization process may be very different depending on which part of parameter space you're talking about. I think there's a fair amount of evidence from both analytic and numerical works that circularization is inefficient when the pericenters are non-relativistic, greater than a few tens of gravitational radii. But when the pericenters are relativistic, apsidal precession is reasonably efficient at forcing shock dissipation at self-intersection points and leading to fairly rapid circularization. But this is very much an open problem. Related open question, which is a little more observationally driven, is the unknown geometry and even power source for the optical and near ultraviolet radiation we see from tidal disruption events. What is puzzling about this is that if you take a sample of optically selected tidal disruption events, like the one I showed you on the past slide, and you assume these things are spherical cows and fit a blackbody radius to them, the blackbody radii that you get are 1 to 2 orders of magnitude greater than the tidal radius itself. As you can see in this compilation from Tiara Hung, I've included right here. This is surprising because if the tidal streams efficiently circularize, you should form a compact accretion disk which extends to maybe 2 or 3 times the tidal radius and is much too compact and hot to emit significant ultraviolet significant optical and near ultraviolet radiation. So one observational surprise, which was evident with the discoveries of the first optically selected TDs at the beginning of the last decade, is that these things are a lot brighter in optical wavelengths than simple-minded theorists expected. There are a couple of possible explanations for this. One is that you do have some sort of circularized inner disk, a central engine that's putting out an ionizing continuum in the soft X-ray and extreme ultraviolet. And this ionizing continuum is getting intercepted by an optically thick reprocessing layer, which is downgrading it to the optical wavelengths that we see. This reprocessing layer could be a quasi-hydrostatic layer of debris, or it could be an outflowing wind. A second possibility is that maybe there's no inner disk at all in some of these TDs, and the power source for the optical emission that we see is actually shock power from internal shocks within the debris streams or self-intersection shocks between debris streams. Right now, this is really an open question and is a hotly debated topic in TD physics. And then finally, we have some interesting rate discrepancies that have been bouncing around for a few years. If you do relatively conservative stellar dynamics calculations to estimate lower limits on TD rates, you get a sort of average rate per galaxy of order 1 disruption every 10,000 years. But this is, even though this is a small number, it's about an order of magnitude higher than the rates that observers have been inferring for a long time. Likewise, or conversely, I should say, there's a bit of an opposite problem, which is that TDs are very overrepresented in rare post-starburst or E+A galaxies. And in fact, the inferred per E+A rate of tidal disruption events is very high, of order 1 disruption every 1,000 years, posing some interesting puzzles for stellar dynamicists. Now, there are a lot of different reasons to study tidal disruption events, many more than I can fit into this talk. The evolution of the inner disk in a TD probably goes from super Eddington to very sub-Eddington accretion rates over timescales of months to years, making these natural laboratories to test open questions in accretion astrophysics. We know that a subset of TDs also launch relativistic jets, So we can use this subset of TDs to probe questions about jet launching mechanisms and to understand something about the circumnuclear medium, the ISM on subparsec scales in quiescent galaxies. People or theorists have speculated for a long time that the TDs which launch relativistic jets may also be major sources of interesting astroparticle events, such as ultra-high energy cosmic rays or PeV neutrinos. And in fact, in this past year, 2020, we saw the first tidal disruption event, which was spatially and temporally coincident with a high energy ice cube neutrino, which was very exciting. TDs may also serve as electromagnetic counterparts to low frequency gravitational wave signals that will be seen by future detectors such as LISA. I could give entire talks on all of these subjects, but our motivation today will be using TDs as probes of supermassive black hole demography. So using observable properties of TDs to back out masses and spins of supermassive and I should say also intermediate mass black holes. So let's start by thinking about how TDs can be used to probe black hole mass. And in the back of our mind, we can keep this wonderful plot from Marta Voluntari as motivation for this exercise, which is that if we could get a better handle on the bottom end of the black hole mass function in galactic nuclei, we could start to answer lots of astrophysically interesting questions, such as disentangling different seed formation scenarios for high redshift massive black holes, as you already heard about in the first day of this conference. So let's start by talking about ways that optical and near UV emission can be used to constrain the spins of massive black holes. As you've already heard, we don't really understand fully the power source for optical and ultraviolet emission. So different theorists with different models have different ways to turn observed optical light curves into constraints on the mass of the underlying black hole. For reprocessing models, the most popular and I think the most well-developed tool for converting multiband photometric light curves into black hole mass estimates is this code MOSFET, developed and used mostly by James Guillauchon, Brenna Mockler, and their collaborators. Brenna is going to talk more about this later in this session, so I won't say too much about this, except to note that although MOSFET is the best tool we have right now for converting optical light curves into mass estimates, under the assumption that the optical light curves are reprocessing powered, we still don't understand in a first principles way the geometry and time evolution of the optical photosphere or the time evolution of the accretion rate in the central engine, which is supplying the ionizing flux to be reprocessed. So we have to make phenomenological assumptions about these things if we want to back out black hole masses from optical light curves. The same is true for theoretical models which assume that the optical emission is shock powered. There was a nice recent paper by Taeho Ryu and his collaborators introducing an analogous kind of simplified algorithm, TD mass, to back out black hole mass from optical light curves in the shock power paradigm. But again, this requires you to make fairly significant, I would say, phenomenological assumptions about the geometry and time evolution of the photosphere that is observed. So if you make these assumptions, you can get black hole mass estimates. And I think looking towards the future, as 3D hydrodynamic simulations improve, we'll be able to calibrate these assumptions much better off of real first principles calculations. But for now, I think we do need to keep these assumptions in the back of our mind. I should say also that there are more indirect methods for estimating black hole mass in an individual tidal disruption event that rely on galaxy scaling relations. And while these give you a rough handle on the mass of the underlying black hole, in some sense, they sort of defeat the purpose of this exercise, which is to come up with an independent way to estimate black hole masses from this new class of transients. Okay, so if you use these tools, MOSFET and TD mass, you see that the masses that you estimate for the underlying black holes are reasonably consistent with these sort of classic galaxy scaling relations. which tells you, hopefully, that these tools are pointed in the right direction. But ultimately, you really do want to see, in the future, I think, a sort of first principles validation of the underlying assumptions about the geometry and evolution of the photospheres. So a different approach to backing out black hole mass from observed TDs is not to look at the optical emission, which, as I've already mentioned, is not so well understood, but instead to look at the quasi-thermal soft X-ray emission, which is present in a subset, not all, but a significant subset of tidal disruption flares. And I'll freely admit my own bias here. This is something that I've been pretty active in for the last couple of years, because it seems to me that there's less theoretical uncertainty about the origin of the quasi-thermal soft X-ray emission. To my knowledge, there's only really one explanation for this existing in the literature today, which is that this soft quasi-thermal X-ray emission is coming from the inner annuli of some sort of quasi-circular accretion flow near the ISCO of the underlying black hole. The X-rays that we see in a significant fraction of TDs are very soft, very thermal, analogous to the high soft state of X-ray binaries, and pretty dissimilar from the X-ray spectra of most AGN out there. What this means from a practical perspective is that you can take a popular tool used in the study of X-ray binaries, which is X-ray spectral continuum fitting, and use this to constrain properties such as the mass of the underlying black hole. This X-ray continuum fitting approach is something that's been done for a number of years for X-ray luminous tidal disruption events. For a very exciting example of this, see Jiacheng Lin's past work. And one thing that helps you in relation to past attempts to use continuum fitting on AGN is not just the fact that you have this very soft quasi-thermal spectrum, but also the fact that the accretion rate varies by orders of magnitude across a few years of observation, which helps to break degeneracies that plague continuum fitting attempts on sort of classic slowly varying AGN. Motivated by this, my collaborators and I, Peter Yonker, Ann Zabladov, and especially Xixiang Wang, a postdoc at the University of Arizona, have been trying to work in a systematic way to do this kind of X-ray continuum fitting to extract properties of black holes that power tidal disruption events. What Wen has found is that multi-epoch X-ray continuum fitting is capable of giving very tight joint constraints on the 2D parameter space of black hole mass and black hole spin. The approach that we take is to use general relativistic slim disk models. So these are the slim disk generalizations of the classic Novikov-Thorne solution. We assume that we don't understand the circularization process fully, so we don't make any prior assumptions about the time evolution of the accretion rate. This is something that we fit at each epoch of X-ray observation. We then plug our models through a Kerr-metric ray tracing code, assuming that the emission from them is a spectrally hardened or incompletely Comptonized black body coming out from each annulus of our accretion disk. And I should mention that there are other possible ways to use these X-ray observations to constrain black hole mass and spin. I'll come back to ones related to QPOs in a few minutes. But first, I want to show you some early results from our continuum fitting efforts. So here is the joint constraint on mass and spin for one TD we've studied, Assassin 15OI. The colors represent confidence levels in our constraints. So blue is our 1 sigma confidence contour, purple is our 2 sigma, and so on. And the vertical lines represent constraints on the mass from other means. The black lines are the mass constraint from the M sigma relation, and the red lines are from Brenner-Mockler's work on this flare using the MOSFET code to estimate the mass from the optical light curve. And what you can see is that for this flare, we get some kind of constraint on the black hole mass, but it's not particularly tight, and we're not able to constrain the spin at all. Part of this is because we don't have a lot of X-ray observing epochs, and another part is that we think this is a nearly edge-on accretion disk. The picture gets much better if we go to accretion disks that are not edge-on, where we have more data. So here's the same kind of joint constraint for Assassin 14Li, where we actually had 10 XMM Newton epochs to play around with. Here you can see that we get a very tight constraint in the two-dimensional plane of black hole mass and spin. The individual 1D constraints are good, although not as tight. But if we have a different mass measurement, like optical light curve fitting to break the degeneracy, then the ultimate spin constraint gets very tight indeed. I should also mention that for, I think another promising frontier for extracting black hole masses from tidal disruption events is going to very late times. So even though there's a lot of uncertainty about the hydrodynamics at early times in TDs, most theoretical models seem to predict that if you wait long enough, eventually you do circularize these debris streams into something that looks like a classic accretion disk. So if you wait long enough, this disk will enter a slowly evolving, viscously spreading state, which can be modeled fairly well with just a time-dependent 1D hydrodynamics approach. This was first done by John Canizzo, wow, almost 30 years ago, quite a while ago. These late-time, slowly evolving disks emit extreme ultraviolet, maybe some soft X-ray from their inner annuli, and they're very bright in the far ultraviolet at their outer annuli. You can see an example of this in our far ultraviolet HST campaign in the picture on the right of this slide. This was work led by my observational collaborator, Sjoerd van Velzen. And here you can see that you have this complicated early time light curve with a rise and a fall. But in many TDs, this light curve flattens out once you start talking about timescales that are 5 to 10 years after the peak of the flare. And that indicates a transition to this slowly evolving, viscously spreading accretion disk. There's been a lot of great work done in the last couple of years by Andrew Mummery and Steve Balbus to try and turn these late time observations into constraints on the black hole mass. You can see an example of that here. So in this work led by Andrew Mummery, you see the complicated early time UV emission, which we don't understand very well. They fit it out with a power law, but then their very slowly evolving, viscously spreading disk model, which depends on the mass of the black hole, does a good job at fitting the late time light curve and enables you to get constraints on the black hole mass. Okay, that's the mass of black holes. Now let's think about their spins, which again is a little bit of motivation in this figure that I think many of you have seen before. If you know the spin distributions of massive black holes in the universe, that gives you a key piece of information about how black holes grew over cosmic time. So let's see if we can learn something about spins from tidal disruption events. I'm running a little low on, well, okay, I'll show this movie quickly. So this is a movie very similar to the one I started off this presentation with, except here, instead of assuming an adiabatic, inefficiently cooling equation of state, we've assumed an efficient cooling equation of state for the relativistic tidal disruption event that we're simulating. And what you can see is that if the debris streams are able to cool efficiently, as may happen in TDs around high mass black holes, then the spin of the black hole is capable of delaying the circularization process substantially. Lens-Thirring precession winds these dynamically cold debris streams up into this beautiful, very complicated three-dimensional structure and delays the formation of an accretion disk by up to an order of magnitude or maybe even more. Eventually, you do circularize the debris streams after you have grazing shocks between the streams that have been spun up or precessed into different orbital planes, but it takes about 20 times longer than it does in the first simulation with inefficient cooling that I showed you guys. So, okay, we've already discussed how X-ray continuum fitting gives you a powerful way to constrain the spins of supermassive black holes and TDs, but it's a way that does have some degeneracies with black hole mass. These circularization delays offer another approach, but they depend in a sensitive way on these messy details of time-dependent relativistic hydrodynamics, which we still don't understand fully. Another interesting possibility involves X-ray QPOs. So the accretion disks that are formed in the aftermath of tidal disruption are born at kind of an arbitrary inclination angle. Since they're thick disks, the response to a misaligned length-Thuring torque at leading order will be to precess around the black hole spin axis like a solid body rotator, which could give you a low frequency X-ray QPO with a period of days to weeks, maybe months if the black hole is slowly spinning. On the other hand, even though these low frequency QPOs haven't been convincingly observed yet, what observers have convincingly seen are very high frequency QPOs with periods of order, with periods that are comparable to the epicyclic period at the innermost stable circular orbit, or ISCO. So these high frequency QPOs are very exciting because we know that they exist. But on the other hand, we don't have a compelling theoretical interpretation for them yet. So I think this is an interesting frontier in constraining the masses and spins of black holes in TDs. But then there's a final way to constrain black hole spins in TDs, which is not dependent really at all on anything you assume about hydrodynamics. It's a purely dynamical constraint. So I'd like to spend a minute or two talking about it. This constraint boils down to a concept known as the Hills mass, which comes from the fact that the tidal disruption radius scales as the black hole mass to the 1/3 power, but the Schwarzschild radius, or the event horizon of the black hole, is of course linear in the mass of the black hole. So what this means is that if you turn your knob and increase the mass of your black hole, eventually the tidal radius for any main sequence star will recede inside the event horizon, and you won't anymore be able to produce an electromagnetically luminous flare. So if you do this calculation in Newtonian gravity, or in an exact general relativistic way in the Schwarzschild metric, you find that for main sequence stars, this critical Hills mass separating luminous from non-luminous TDs is about 10 to the 8 solar masses. But if you do the Hills mass calculation precisely in the Kerr metric by computing a relativistic tidal tensor, which is really just a projection of the Riemann tensor onto a co-moving orthonormal tetrad, you find that the magnitude of this Hills mass changes by almost an order of magnitude as you go from a non-spinning Schwarzschild black hole to an extremal Kerr metric black hole. There are a couple of reasons for this. You can ask me about them later if you're curious. But what this means is that if you see a TDE from a black hole of order 10 to the 8 or 10 to the 9 solar masses, thanks for the time warning, Patricia, then the fact that you saw a TDE at all enables you to come up with a lower limit on the spin of the black hole at the center of that flare. So here you can see an example of us, my observational collaborators led by Georgios Louloudis, making this kind of Hills mass argument for the famous, albeit controversial TDE candidate, Assassin 15LH. Assassin 15LH came from a very old galaxy with no ongoing star formation. It's unlikely the stars in the nucleus of this galaxy were larger than 1 solar mass because of their advanced age. In gray, you can see the mass of the black hole as predicted by the M sigma relationship. So if the M sigma relationship is valid in this galaxy, in order to get a tidal disruption, you need a spin that tracks the colored curves that are shown. So assuming the best case scenario for tidal disruption of a 1 solar mass star, this is the best case in a very old stellar population, you need a black hole spin that is at least 0.6. So what I like about this technique is it doesn't assume anything about complicated hydrodynamics. It's a purely dynamical way to put a lower limit on the spins of supermassive black holes. Okay, so far I've talked about what we can do with individual TDs, but in the last 5 minutes of this talk, I'll briefly touch on what we can do with populations of TDs, which we expect to see in large numbers in the near future. To begin, I'll just say that the way in which we use stellar dynamics to estimate TD rates in individual galaxies is a somewhat complicated procedure. It dates back to pioneering work in the 1970s that was first applied to realistic observations of galaxies by John Megorian and Scott Tremaine in the late 1990s. The basic idea is that stars orbiting supermassive black holes in galactic nuclei will be tidally disrupted if some sort of perturbation scatters their velocity vector into a conical region in velocity space known as the loss cone. You can see an illustration of that in the cartoon on the right. What I did in collaboration with Brian Metzger a few years ago was really to build on this earlier work by Scott Tremaine and David Merritt and their collaborators, and take a large sample of HST photometry of nearby galaxies, make a few assumptions, but I should emphasize these are generally conservative assumptions that act to give us a lower limit on TDE rates. And what we find going through this kind of dynamical loss cone modeling is that theoretical rates for how often stars are disrupted in realistic galactic nuclei are relatively high, of order a few disruptions every 10,000 years, maybe up to a few disruptions every 1,000 years. And at the time we wrote our paper in 2016, this was 1 to 2 orders of magnitude greater than the observed rate of tidal disruptions found by time domain surveys. And what's interesting about this is that one of the dominant, maybe the dominant uncertainty on this two-body relaxation TDE rate estimate is the unknown occupation fraction of black holes in low-mass galactic nuclei. The reason this is so important is that it is the smallest galaxies that have a large occupation fraction which dominate the volumetric TDE rate. So in our paper, we assume these 5 color-coded ad hoc prescriptions for what the occupation fraction looks like in low-mass galactic nuclei. The labels at the top of the panel correspond basically to the smallest black hole with a high occupation fraction. And what we get is the following volumetric rate estimate. So this is the number of TDs on the y-axis per cubic megaparsec per cubic year for these 5 different assumptions about the occupation fraction of black holes in dwarf galactic nuclei. You can see that in order to beat the rate down into any kind of agreement with observations 5 years ago, you need to make very, very conservative assumptions about the black hole occupation fraction. You need to assume that there aren't many supermassive black holes below 2 or 3 times 10 to the 6 solar masses, which is arguably in tension with observations already. It turns out, and this will be my last major slide, that the resolution of this rate discrepancy came from the fact that early efforts seriously underestimated the number of low luminosity TDs. In other words, the TD luminosity function was not adequately characterized 5 years ago, and more modern empirical efforts seem to indicate that the TDs we observe in the sky in our current flux-limited samples are really just the tip of the iceberg, and there's a larger, largely unobserved population of low luminosity flares that are missed by current flux-limited surveys. And when you correct for that empirical luminosity function, you find lower limits on the observed TD rate of order 1 disruption every 10,000 years per galaxy, which are starting to come into agreement with the bottom end of theoretical rate estimates and point the way forward to using populations of tidal disruption events to measure the occupation fraction of black holes in dwarf galaxies. I'm just about out of time, so I'm going to skip these 2 slides and go straight to my conclusions. One thing I want to emphasize is that even though our current sample of TDs is modest, just a few dozen flares, in the very near future, the Vera-Rubin Observatory and potentially the eROSITA X-ray survey will find thousands of flares, thousands of new TDs every year. If we can improve our theoretical models for TDs before then, if we can come up with better ways to back out the masses and spins of black holes from observed light curves and SEDs, then this near future sample will be an unparalleled tool for performing a cosmic census of supermassive and even intermediate mass black holes. But there are a number of challenges along the way, so I'll leave those up to hopefully spark a little discussion in the Slido chat. So thanks for listening.